Hello everyone, welcome again in lecture number 7. So, before diving into the technical specifics of Google Colab and AWS, it's essential to establish the broader context of why cloud based AI tools have become so transformative in research settings. The field of artificial intelligence has evolved dramatically over the past decade, transitioning from theoretical concepts explored primarily in academic settings to practical applications deployed across industries ranging from healthcare to finance, autonomous vehicles to natural language processing. So, in this presentation, we will examine how these cloud platforms have transferred experimental design in AI research. So, we will explore not just the technical capabilities but also the workflow considerations, cost implications, and strategic advantages of incorporating Google Colab and AWS into your research practice. So, whether you are developing a small scale machine learning model for a class project or developing a large scale deep learning application for industrial research, understanding these tools can significantly enhance your productivity and the quality of your work. So, when discussing cloud based AI platforms, it's impossible to overlook the critical role of graphics processing units, that is GPU, in modern machine learning workflows. So, what is GPU? GPU is a graphics processing unit specialized in parallel computations, making them ideal for ML tasks. GPUs were originally designed for rendering graphics in gaming and visualization applications, but their architecture, featuring thousands of smaller cores optimized for parallel processing. So, while a CPU might process one or a few operations at a time, sequentially a GPU can handle thousands simultaneously, dramatically reducing training times for complex models. So, in machine learning context, this parallel processing power translates to several key advantages. First and foremost, it enables researchers to train models on larger datasets within practical time frames. So, for example, if you consider training a state of the art image classification model on a CPU might take weeks, while the same process could be completed in hours or days using GPU acceleration. So, this efficiency is not just about saving time, it fundamentally changes the research process by allowing more rapid iteration and experimentation. So, moreover, GPUs facilitate the development of more complex models. So, without their computational power, many of the advances in deep learning, such as convolutional neural networks for image recognition or transformer architectures for natural language processing, would be impractical due to the enormous computational resources they require. The ability to experiment with larger architectures and more sophisticated techniques has been a major driver of innovation in AI. So, cloud based AI platforms provide a scalable infrastructure that can be adjusted. Sorry, that can be adjusted dynamically to match project requirements, whether you need resources for a small experiment or a large scale production deployment. These platforms allow you to provision exactly the computational power you need at any given moment. So, this elasticity is particularly valuable in research setting where resource requirements can fluctuate dramatically as projects evolve. So, these are the benefits: cost effectiveness, scalability, and collaboration. So, let's now explore Google Colab, a widely used cloud based AI platform especially in education and research. So Colab, short for collaboratory, is a free Jupyter notebook environment that runs in the cloud, developed by Google Research to make AI development more accessible. So a key feature of Colab is its seamless integration with Google Drive, allowing users to store and share notebooks, datasets, and model outputs easily. Its familiar Google interface simplifies access for those already using Google Workspace. So you must have idea. Hopefully you are using it in your daily life. So Colab provides free access to GPUs and TPUs, making it a valuable resource for researchers lacking high-end hardware. It supports major Python-based machine learning frameworks like TensorFlow, PyTorch, and scikit-learn, enabling compatibility with modern AI workflows. The cell-based notebook structure facilitates incremental development and experimentation. So with a browser-based interface, Colab requires no local installation and is accessible from any internet-connected device. It also supports real-time collaboration, making it ideal for team projects and classroom instruction. So while Colab offers many advantages, it has limitations also, which we'll discuss later. For now, let's focus on practical steps to maximize its potential. So, these are the practical steps to begin leveraging Google Colab for your machine learning projects. You can follow these steps. So, first one is the create a Google account. If you don't already have one, sign up for a Google account at accounts.google.com. This provides access to Google Drive and Colab. Now, step number 2, access Google Colab. Visit colab.research.google.com to open the Colab interface. You will see a dashboard where you can create new notebooks or access previously saved ones. Now, step number 3, create a new notebook. Click on New Notebook to start with a blank Jupyter Notebook environment. Colab notebooks have a file extension that is .ipynb, similar to standard Jupyter notebooks. Step number 4, connect to a runtime. So before executing any code, you will need to connect it to a Colab runtime, which provisions the computational resources including CPU, GPU, or TPU. Click on Connect in the upper right corner. Colab will establish a connection to a virtual machine in Google's cloud infrastructure. So, step number 5, mount Google Drive. So, for persistent storage of datasets and model outputs, mount your Google Drive to the Colab notebook. Now, step number 6, install necessary libraries. So, while Colab comes with many popular libraries pre-installed, you may need to add additional packages using pipe or conda. Now, step number 7, upload or access data. So you can upload small datasets directly through the file upload dialog, but for large datasets it's more efficient to store them in Google Drive and access them via the mountain directory. Step number 8, write and execute code cells. So organize your workflow into code cells, starting with data loading and pre-processing, followed by model definition, training and evaluation. So remember that each cell can be executed independently, allowing you to test components incrementally. So thus, by following the above steps, you can establish a productive workflow in Colab that takes full advantage of its cloud-based resources while mitigating potential issues related to session limitations and resource constraints. So, let's walk through a practical example of building a conventional convolutional neural network on Google Colab. So we will use the TensorFlow library with the MNIST dataset, which is a classic benchmark for image classification tasks. First, import the necessary modules and load the dataset directly from TensorFlow's built-in datasets. Then pre-process the data by normalizing pixel values and splitting into training and validation sets. Next, define your CNN architecture using layers like Convo 2D, Max Pooling 2D, and Dense. After compiling the model with an appropriate optimizer and loss function, train it using the fit method. Colab's GPU will accelerate the training process, allowing you to experiment with different architectures quickly. So finally, evaluate your model's performance on the test set and visualize sample predictions to understand where the model excels or struggles. So these are the limitations of Google Colab, that is session limits. So it has maximum of 12-hour run time per session, and second one is shared resources, that is its performance variability due to shared GPUs, and third one is data security, so privacy concerns for sensitive research data. That means while generally secure for most use cases, Colab stores your data on Google servers. For research involving highly sensitive or proprietary information, this may raise concerns about data privacy and compliance with institutional policy. So, Amazon Web Services, that is AWS, Amazon Web Services for AI and ML, represents the other end of the spectrum in cloud-based AI development, offering a comprehensive and highly scalable infrastructure designed to support the most demanding machine learning workloads. So, AWS AI and machine learning capabilities are built upon its extensive global infrastructure, which includes dozens of data centers across multiple regions. This distributed architecture ensures high availability, low latency, and robust disaster recovery options for mission critical applications. So, researchers working on projects with stringent reliability requirements or those needing to comply with specific geographic data residency laws can leverage AWS regional data centers to meet these needs. So beyond raw computational power, AWS provides a rich ecosystem of managed services that streamline AI development. Amazon SageMaker, for example, offer fully managed infrastructure for building, training, and deploying machine learning models at scale. It includes tools for data labeling, model tuning, and endpoint deployment, reducing the operational burden of managing the entire ML lifecycle. So deploying machine learning models on AWS EC2 involves several structural steps that require careful planning and execution. Let's walk through this process in detail. So first one is create an AWS account. So if you don't have already an account, then you have to first create, then navigate to the EC2 dashboard and choose an instance type. Then select an Amazon machine image. Configure instance details, set up security and all. So what is the deployment process? Steps for ML deployment on AWS EC2. So instance selection, choose GPU instance type like p3.large, then configuration, then software environment, and then model training, and then performance monitoring. So this is the use case example, deep neural networks, which is implemented advanced neural network architectures using AWS resources. Now, what are the advantages of AWS for AI? It is dedicated GPU resources, infrastructure scalability, security and compliance, flexible pricing. So this is the comparative analysis between Google Colab versus AWS. So in terms of features, we have considered the features: pricing, GPU resources, scalability, ideal use. So Google Colab is free with the limitations, but AWS GPU instances pay as you go. Now Google Colab has limited and shared AWS GPU instance dedicated and high performance provider. Google Colab is limited for scalability, while AWS GPU instances highly scalable. Now Google Colab can be used ideally for education and small projects, while AWS GPU instances can be used for enterprise or scalable projects. So these are the best practices. We can determine resource and scalability requirements in advance. We can prevent overspending through consistent monitoring, and we can choose appropriate instances, leverage spot instances, and shut down inactive resources promptly. These are the references and recommended resources for Google Colab, colab.research.google.com. So you just create an account and go through this website and you will learn. Definitely, it is very easy. Now AWS machine learning, so aws.amazon.com or machine learning. So please go through these links and you can learn all about in practice. So thank you for watching this lecture.